Alright, and welcome to another exciting readings class. Today I would like to introduce you to the midterm. You're in shock, I can see it. Yes, it's true. What we have here today is representative of the middle of the term, and therefore you have to have a midterm. And the midterm will build on the prior work that you have done in preparation for writing a proposal of a thesis. And so what you are going to do for your midterm is to write a thesis proposal. What I have done is I've created a midterm report, and I've made the due date 2 weeks from now. So that gives you sufficient time, I hope, to write something good. And it will be based on the presentations that you've done and the work that you've done before now. The midterm exam is written. It's handed in hard copy, unless you're trying to do this distance learning or you're sick and you want to just do PDF. My preference is to sit down in my easy chair with my red pen and to go over it in detail and copy edit it. And if it's going to require a lot of copy editing work, it will be reflected in your grade. So have a friend look at it, make sure it's well written and there aren't a lot of problems with the writing. Writing counts in this course. One of the primary outcomes of this course is that you improve in both your oral and written communications. This paper represents a substantial outcome showing good writing. Therefore, it must be fairly well written. So, here's what you need for your midterm. A draft of a thesis proposal. I would love to have the printout before the class begins. You need a title page. You're going to list your name, the title of your thesis, the title of your advisor. In my case, it will be me. And the problem statement has to be present. So the problem statement has to be a well-formulated problem statement. Given some situation, subject to some constraints, we intend to find a solution. Right? So, for example, given appliances which do not communicate their power usage, we are subjected to the constraints that we don't want to draw substantial additional power. We want to be able to have a mechanism by which we can communicate that usage to some central location, and we seek to find a unique solution to this very important problem. You can justify the problem with what's known as the section on motivation. And that motivation section is going to include some reason why there is going to be societal impact for your problem. Why do people care? Then there's this thing about your approach. And you may say, well, in the past, people have had outlets which have measured power usage and have communicated to a central hub. But these solutions have been inefficient for a variety of reasons. But my solution is better because. So my solution is just like theirs with a difference. And the difference is, you tell me. I haven't been able to establish that difference, but that difference will represent your contribution, your inventive step, your reason why your thing isn't obvious. And maybe you're going to combine technologies from Z-Wave and fractal antennas and power over Ethernet and power over carrier current and quantum torpedoes, whatever it is you're putting in there to make it work better. I made that up, okay. There won't be quantum torpedoes. But quantum torpedoes are different from photon torpedoes, or so we are led to believe. if they existed, we'd be saying, yeah, gotta get me some of those quantum torpedoes. So you have these different approaches that you may take. You're going to list them. There's going to be risk in this thesis proposal. Risk is an interesting point. When people determine if your project is worth funding in the world of business, the first thing they'll say is, what's my return? What's the risk to getting this engineered properly? And what's therefore my expected return on my investment? So if you told me, well, the return is $1 billion because it's $1 billion market, but there's a 50% chance that this won't work, then somebody will say, well, it really doesn't have an expected return of $1 billion. Maybe it's only $500 million, because you have to put in that expectation that this might not work. And then you might say, oh, and there's a 20% chance that nobody will want it. So now you take that, $500 million and you prorate it by 80, and then you go and you do it again with the next thing that gives you uncertainty. So there's risks. Got to spell them out. You have to say that before this proof of concept thing that you're embarking upon is done, you expect to have data that shows why your thing is better than the other thing. That is sufficient in terms of a patent. If you have something which looks trivial because it's really just like what everybody else did, but you've got a solution that performs better, that's substantial, and that can make a patent allowed. And it certainly is a way for you to lay claim to your contribution. Here's what I did that's different. It's not just like everybody else's power outlet monitoring thing, because mine does X, whatever X is. Maybe it uses carrier current communications instead of Zigbee or something. I don't know. So then you're going to have these so-called ethical issues, right? What about safety? What about, I'll call it standards? Isn't there an electrical code? Does it have to be UL listed? Is there a NEMA regulation that governs this device you're going to be creating? These are kinds of questions that have to do with what happens when I take this outlet, modify it with your thingy, and then my house burns down. Ancient Babylonian law from the 1700 BC had a code of Hammurabi. And in the code it said, if you build a house and it falls and kills the owner, then you're put to death. Of course, in this country, all we do is sue you. Unless it's negligent, then you go to jail. So, in general, don't get sued. This is very good legal advice. And don't go to jail because you won't like it. So there are these things that we need to pay attention to, and one of them may be the codes that govern what happens when we plug something into an outlet. So that's not just a safety thing, that's a legal thing, it's an ethical thing. It's one of those things that you have to think about as an engineer when you devise a product, because, and this is kind of an interesting idea, you will be held responsible when you start to sell this product. It becomes a source of liability for you and your company. So if you build a helicopter and it falls out of the sky, you hope that there was a professional engineer who signed off on the software that you wrote while you were an intern that summer. Because if the fire and forget mechanism on the Comanche helicopter fires and forgets on 14 targets, only half of which were not friendly, then you've got a problem. And if the problem has been traced back to the code that you wrote sloppily because you went out to lunch and then forgot to fix the bug, they will find you. They'll sue everybody with any money, and certainly Sikorsky and maybe even the engineers if they have deep enough pockets. They'll be held responsible. But if you've got a small company and you're selling this thing, right, maybe on Kickstarter, and now all of a sudden people have problems, short circuits, burning down houses, melting outlets, you're going to hear about it big time. So that's a I'll call it code of ethics ramification. We really haven't talked about that yet. Has everybody here had an ethics course? No. Probably you have to have a little lecture on ethics, because professional ethics for engineers is governed by rules of behavior which are handed to us by our profession. So it's not just legal stuff, it's also stuff that has to do with when you belong to a profession, the way you behave. Then comes the thing that you've been working on for today, your papers, the historical review, the literature you've cited. You'll want those 18 to 27 papers that you can find relevant. You want to discuss the methodology for each paper. Each one takes a different approach. The data that the paper has presented, and maybe what's called a taxonomy of approaches. Oh, what's a taxonomy? No idea. Well, for example, if you had to organize the animals, you might say that we have animals, and then underneath we have mammals, and we have reptiles, and we have fish. Mammals are not reptiles, reptiles are not fish, mammals are not fish. Mammals have properties which are inherited by all mammals. They have hair, they give live birth, they have milk, and underneath there is humans. Now, there is also whales and dolphins, and certainly they are kinds of mammals. But whales are not humans, and humans are not dolphins, and whales are not dolphins. So, in effect, what we have is an acyclic directed graph. That is a taxonomy, representing subclasses. And that's where we get the classification system used in Java and C++, and C# for that matter. So when we look at classes, we see the cardinality of a set which is larger than the cardinality of the subset, because the subset always carves out a non-intersecting area from within the large set. I could probably draw it on the board, but then nobody would see it if they were doing distance learning. So as I see it, the class-subclass system that we have in Java is an AKO hierarchy, or a kind of hierarchy. And inheritance occurs just the way it would in any way that you would organize a taxonomy. You can do this organization of taxonomies any one of a number of different ways. You could have sensors, and you could say, I have two kinds of sensors, 3D and 2D. And you could say, well, I have two kinds of 2D sensors, active and passive. And I can have two kinds of active sensors, those which use energy that is based in pressure waves, like sound, and those which use energy which is based in electromagnetics, like radar or light. And you could then proceed to divide the taxonomy again and say, well, in the sensor world, you know, those that use sound, we have those that have a ping, right, which are going to be active. But there's also a way to do sound that doesn't have a ping, a passive sound, where you just sit and listen. And you can try and do sort of arranging in that way. Similarly, with vision systems, which in general use electromagnetics, you can have active, where they use like a laser stripe, and then they try to identify the mesh that's used for the target. And they have passive. That's the one we use when we try to arrange in 3D with our eyes. Binocular vision system. Stereoscopic. So in some sense, it's not clear. Should it be active passive? Or should it be 3D 2D? Or how should I divide up the hierarchy? There's no right answer there. Both can be correct. You could say, I'll divide up the hierarchy as 3D and 2D, but then you find out there's a lot of crossover between active and passive as you go from 3D and 2D. So maybe it should be a different hierarchy. It's not clear. So you have to decide that on your own. Let's see now. So you've got this separate section with the listed references, and you're going to cite them based on some sort of annotation, and this is the one I favor, where you list the author, at least the first one, and then perhaps a date. And if there are many authors, you say et al. Just to show that there are others, and that's sufficient. Later, when you go to look at the list of authors, you'll see the whole thing, Aho, Hopcroft, and Ullman. Right, you'll see them all. It'll be spelled out somewhere. And probably you're going to want to summarize your presentation with at least the four most important papers that you found. So we won't have to see them all, but we would like to see at least 4 of them, I think. That would be reasonable. So that's what I'm hoping for your midterm. You've got 2 weeks to do it, and of course you've got something due today, and you'll be doing a presentation today as well. One of the things that I think is most important in any thesis, whether it's a master's thesis or a PhD thesis, is a clear identification of the problem. So problem statements are not something you're born knowing how to write. And so I like to focus on the problem because this is what identifies your contribution. This is the thing that you're really trying to solve, and it shouldn't be guesswork after you're done with a presentation. So what's your contribution? If they're asking that, then you really failed to communicate. So here's the problem, here's my solution. This is going to be kind of like what other people have done with a difference, and the difference is I'm doing X, whereas everybody else did Y. So it's not wrong to do smart outlets just because other people are doing smart outlets, as long as your approach is different. And in fact, in some sense, one could make the compelling argument that there is a strong commercial unmet need for smart outlets, and that in and of itself is a secondary consideration for the patent examiner when they go to determine whether your solution is obvious. So non-obviousness gives you an opportunity for what I will call a secondary consideration. And we can see that when we look at the patent examiner's manual. Patent examiners get trained. They get told by people in the patent office how to apply patent law. And we can even examine what they are told. We can get insight into the mind of the patent examiner when we look at what is considered obvious and what is not obvious. And we can even get insight into how to respond in an appropriate way to an office action in case somebody comes back at us and says it's obvious, it's trivial. It's a midterm. Midterms count for a third. Okay? Homeworks count for a third in average. That's all of them together. And your final will count for a third. That's how the grading is done here. So you have to keep working as you go through this term. You can't leave it all to the end. And if you, have a deadline due in 2 weeks and you let it slip because you didn't start early enough or whatever, I mean, that's bad because you're losing 10 points per day on something that's worth like a third. So think about 3 1/3 points off your raw score. So don't leave it to the last minute. Writing is hard. Writing is one of those things that will hang over your head like a bad homework assignment for the next 2 weeks. So start it early, or you're going to feel badly about yourself. That's my advice. Also, in the event that you want me to review your work before you submit it, I'm very happy to do that. So it's to your advantage to show it to me. I won't grade it, I'll just comment on it, and you can see if you're on the right track. We have a writing center. They can look at your stuff too. And so if you feel like your writing isn't really good, you can go to the writing center for that. So that's a, I don't know, how can I say it? As detailed a description as I can give you, but I can also do better. I can do better because I can give you examples. And you've probably seen some of the examples on the web. If you go to docjava.com, and then go to courseware, thesis work. Here's a bunch of thesis proposals and theses. These are all proposals. So you can look at those. These are all finished theses, so you can look at those as well. So you've got an opportunity here to get some insight into what some of the others have done. Let's see. I haven't seen this one lately. Nice title page, a good abstract. It's the Power Toad. Power Toad uses a buck boost regulator. Here's the basic outline. Alright, same outline. You can borrow this outline. You can even download the Word document and edit it if you like. But, you know, change the words, because if you don't want to do this, if you hand in Power Toad, you don't get credit. Then there's a problem statement in here somewhere. Yep, there it is. There are problems in here that have to be solved. Constraints. Here's an approach. This is like a little product. Power Toad. Here's some prototyping that was done. Motivation and approach, it's all in there. Societal implications, why we care. The safety issues. Probably could have beefed that up a bit, but this is just a proposal. And looks like we've got a nice historical survey showing some different approaches to doing buck boost converters. Power Toad is a DC to DC converter. And looks like there's a few designs. The milestones are good because it gives us an idea about what to expect. This student did not write a thesis. This is not a thesis. This is a thesis proposal. And this is the kind of thing you may end up with when you're done, right? Your project outline, your ideas, the risks involved in doing this research. You have to convince management to back you if you're doing what's called intrapreneurship. If you're working at a company and you're trying to take the technical lead, you've got to pitch to management the idea. Make your case. How do you do that? Well, this is the way I would go. Come up with substantial numbers and a good approach and a background that gives you a way to solve an important problem. Show why the problem is important. Show your approach looks feasible and could work. Management can back you. And then you can have the lead. And look how many things were cited here. 42. I haven't seen this proposal in a long time. I haven't looked at it. This is one of the reasons I brought it up. But it's not bad. The other one's also for you to look at. You can also look at the full-blown theses. Those will be interesting too to look at. So here's a thesis. I got motivation, historical review, which is long, very long, and then I think we get the theoretical background here. This is a little bit more than you would do for a proposal, quite a bit, because this student worked on this for 3 semesters. And they built stuff. In here there should be like a picture of some of the stuff they built. Well, this software here, this electrodynamic software for modeling, they wrote that program. So that enables them to do microstrip array current analysis for a finite element mesh. The so-called new electromagnetism relies on computers. You need computers for new electromagnetism. Here's another one where he does a mesh for Helmholtz regulator and then a microstrip array. You know, if you had this software and fractal antennas, you could predict their performance. Let's see what else we got in here. It's kind of cool, actually. Here he builds it so he gets what's called experimental validation. You could almost see fractal antennas coming out of this. Right? Only here he's just got loops. And so he's going to actually measure with this little device. And he actually went out and bought this. This is like an expensive device. And then he proceeded to measure the performance of his various antennas to see if he could validate his predictions. So that's pretty cool, actually. Cool thesis. And it goes on and on. This is page 80. I think that's a record for me. I haven't had a student do an 80-page thesis like this before. My thesis was longer, but you know, it's not a contest. But if it was a contest, I win. So this is the interesting thing, I think. If you need to do diagrams, there are interesting ways to do them. I have this program which is free called Inkscape, which will let you do diagrams. There's probably does everybody have a way to do diagrams? Pictures? You know, if you're going to do a patent, you have to have very clean images. They used to require that they be drawn with Indian ink, dark black lines. But now, here in the new age, everybody uses CAD tools. Inkscape is interesting because Inkscape can output scalable vector graphic files. So you don't want bitmaps, you want vectors. And so if you're using scalable vector graphic files, you can output them to laser cutters. So you can find what they call the thing universe, and you can download SVG files and then use those designs, modify them a little bit, and then output them to local laser cutters, and they'll cut stuff in whatever you like. Steel, cardboard, plastic, and then you can proceed to actually have things that you can put together. So that's kind of an interesting idea. You know, here in the new age, you just find somebody who does it for you. They outsource it, you give them the designs, and they send you back product, and then you can make a lot of these things. With laser cutters, you don't need to make a mold to do injection molding, which is actually much cheaper, but has a high startup cost. Think like $7,000 to $10,000 to make things that really only cost you maybe $1 worth of plastic or less. So it works, you know, that works out if you're making over 1,000 of something and you can charge $10 each. Then you recover your costs. But in general, if you're not making 1,000 of something, you're better off with the laser cutter. Good for prototyping, too. What do people use for drawing pictures? How do you guys draw pictures? Paint? You cannot use paint. It's bitmap. Don't use paint. Bitmaps are bad because what will happen is they'll print at the resolution of the screen. So you'll get 72 dpi images. Your lines will have jaggies. Nothing will look smooth. What else do you use for your images? Basic line drawings is what I'm asking about. Like that. That should not be a bitmap. Right? This should be like a smooth, clean line. Right? Not a bitmap. Done at any scale on a printer, it should just look nice. So my contention in all of this is that you should be able to have high order curves like this one. That's a cubic Hermite polynomial, in case you're wondering. The reason I know that is because it's controlling the derivatives at the endpoints, as well as its initial and final position. To have that much freedom, you need at least a cubic. I think you can fill it in too. Let's see. Yep. So it's not a bitmap, and it'll print cleanly. In the world of laser cut, by the way, if you do an outline and make it blue, then it cuts it. If you do an outline and make it red, then it makes an etch. So it'll etch in like whatever you like, if you want to etch in your name or your logo or something like this. And for acrylic that's a millimeter, they won't etch it because it's too fragile and too thin. But if you go to 1/8 inch or 1/4 inch, then it'll etch it and you can write stuff, which is fun, especially if you're seeking to prototype a case for your next project, or gears, or whatever you need to make things work properly and get your prototype out the door. So I like this because, why? Well, there are a couple of reasons. The first one, it's free. Free is good. I really like free. The second is it works on all the platforms that I care about: Windows, Unix, and Mac. So it's multi-platform, which means I have a nice portable tool that I can share with others. The third, I think this is kind of cool. There are books about this. I just ordered 4 books from the library just on Inkscape. So you can get lots of documentation online in the form of books, and so that makes it sort of a popular tool. The fourth, I think this is kind of an interesting idea, that you'd be able to quickly prototype your product, whatever it may be. Its case, the gears, the things that you need to make stuff, all with a 3D laser cutter. Or it'll also output STL, so you can go to a 3D printer like downstairs. But that 3D printer, you know, it makes everything kind of pasty. And I like, if I want a clear case that I can show people, I want something that looks nice. You know, make it out of acrylic. Get the laser cutter. So, you know, you can't manufacture things from a 3D printer. It's too expensive. You can't make 1,000 of something. You can make 1, maybe a couple or 3. But you don't want to make 100 or 200 because the materials are too expensive. So it's not a good way to manufacture. So there it is, little program for drawing. but maybe you have a better one. Visio, CorelDRAW, Adobe Illustrator. You got to pay for those. They're not free. And not only aren't they free, they're very expensive. Hundreds of dollars, if not thousands, some of them. Oh, and I think this one is open source, too. There's another one people have been using around here. I think it's 3D, SolidWorks. Also not free. Also very expensive. But at least it's here. But if all you want is simple diagrams, I think SolidWorks is overkill because it's 3D. So what do you think about the midterm? Maybe I spent too much time talking about it, right? But if you spend some time writing and then you bring a preliminary printout next week, I will look at it. So maybe it's good that you start it and I take a little time and talk about it now. Are there any questions about the midterm? Well, any questions you want to bring next week, I'm very happy to answer in class. And if you want to, we can get together outside of class as well. But might as well ask the questions while you're here. Anyways, there it is. The midterm, such as it is. Now I thought maybe what I'd do is take a little time and talk about this idea about the prima facie case. Prima facie means on the face, at first blush, some people would say, or the first look. I gave the patent, and this is the training that's given by the patent office to patent examiners. I found this by Googling a bit, and then I said, oh, this is like a gold nugget. I have to show this to my class. And I went over it, and I said there are certain things that we didn't really cover in this class, and things that are obvious to a patent examiner are not going to be obvious to you. It's a legal concept, this prima facie obviousness. It's a procedural tool used by the examiner, and he can apply it to anything. And what you want to do is you want to start by saying who has to make the case, the prima facie case, and the answer is it's really up to the examiner. But once they make the claim of obviousness based on a prima facie case, then the burden falls to you, because now you as the applicant must respond to what is now called the office action, the one that says it's trivial. So the obviousness was claimed by the examiner, and presumably the examiner has supported the assertion. They can't just say it's obvious. They have to say it's obvious because. Power outlet monitoring is obvious because you can already buy power outlet monitors from Walmart. Why on earth would you want to build another? But, on the other hand, if what you said was power outlet monitoring isn't what I'm claiming. What I'm claiming is the use of fractal antennas to communicate between power outlets, and that's never been done before, then maybe that's something that you could do. But then you have to duke it out with Raoul over there, who says, no, that's mine. You can't have my idea. So then, but of course, we're in a first-to-file country. So if you run to the patent office, you can probably get the patent on that. On the other hand, there are already fractal antennas out there. But yours will be different because it's for power outlets. So you'll have what's called an improvement patent. So the examiner has to prove the case, or make the case. And if they don't, then you are not on any obligation to submit non-obviousness evidence. However, it behooves you to make that case when you apply for the patent, to show both primary and secondary reasons why your stuff isn't particularly obvious. Why it's important, perhaps for commercial reasons. And maybe you could even make the claim that other people have been trying to solve this problem for a very long time, and I've got the solution. And therefore, it's not obvious. That shows people who are skilled in the art weren't able to solve the problem, but you did. There are these things which you can show if the obviousness thing is concerning you. Compare your data with somebody else's. Oh, I've got, a car, and it uses gas. Huh, that's obvious. But my car gets 100 miles per gallon. Ah, that's important. That's not obvious. How do we make a car get 100 miles per gallon? Okay, now we're paying attention, right? So the performance data on the car is very interesting. And the reason it gets 100 miles per gallon is it only goes 30 miles an hour. And it weighs as much as a scooter. And it only has 2 wheels. And it's really just a bicycle with a single little engine that you could use for a model airplane. Okay, maybe it became obvious again. So at some level, one could say it's really not a car. It's more like a bicycle, and you have to pedal it. Or you have to use your feet to give it a push. Okay, that's not a very good car. So there's this other thing about commercial success. If you are looking at this long-felt but unmet need, that's a big deal. People have been trying to do this 100-mile per gallon car for a very long time. So maybe that's some interesting thing about that. If you said to me, well, all of these communicating power outlets are sucking down a lot of power, and that defeats the purpose. They're not very green. They're always using power. But I have an approach that puts the microprocessor to sleep and only wakes it up every 2 hours to do a monitoring. Now, all of a sudden, it looks like maybe you've got a different approach, maybe. So if you said, gee, it only uses a few nanowatts every minute or two, and then it adaptively samples, and I've got a new algorithm, maybe that's the contribution. So I need to know what your contribution is. It has to be clear. It'll be part of what's in the claims. It may not be just, oh, I've got another Weetricity thing, but it's Weetricity with a difference. And the difference is we are identifying the Hausdorff-Besicovitch dimension of fractality that enables us to optimize power transfer. And we can even go through and say, and I expect to collect data that allows me to compare a Sierpinski carpet with a Mandelbrot set, or a Julius set, or 7 other sets. And I'm going to be able, through this exploration and experimentation, determine empirically which are the best antennas, and maybe even come up with a good theoretic reason why they're better. Then all of a sudden we've got a contribution to the field. A theoretic reason, which may not exist, about why fractal antennas of certain kinds are working better. A characterization of the limits of recursion. You could say, well, geez, after 10 levels of recursion, the antennas don't improve. Maybe I only need 3 levels of recursion. So then all of a sudden you say, gee, that's important. People didn't know that before. Another contribution to the field. So your ability to characterize the antennas and show which antennas are better and under what circumstances, that can make a big difference. Now people have guidance on how to embody the power transfer problem. I'm forgetting what all the theses topics are. George was force fields, right? Force fields. That I don't think that. See, now that's interesting. If you can say there is no real unmet need commercially because no one really needs force fields just yet, but you've created one you could definitely get a patent. No question about it. But if nobody can use it for 100 years, you're a little early. So it's not clear. Right? I mean, it's like quantum mechanics. You know, people weren't sure that they could use it, but now it's got all kinds of applications. Same thing with like Higgs bosons. People don't know where they're going to be used yet, but I have no doubt that within 20 years there'll be all kinds of applications. And if you ask Clerk Maxwell, why are these equations important, these electromagnetic field theory equations, he'd say, they're just interesting mathematically. I have no application. And yet, when we look at them now, they are the most profound equations used everywhere in electrical engineering. So this is one of those things where, you know, you can be too early. I don't think Clerk Maxwell got a dime from his electromagnetic field theory. I don't think he made any royalties on that. But it was very important. So he could have probably have patented it, but you know, it's kind of, you can't patent the sun. You can't patent things that you just discover that are physics. So you'd have to have some kind of an embodiment, like an antenna design. So when a patent examiner looks at your stuff, they're going to look at these rejections, they'll look at the code, and they'll try and figure out why they can come up with a rejection that's airtight. In a sense, they're acting as the critic and you're acting as the artist. You're creating, and they're just being critical. And that, in that process, what happens is you have to essentially cater to their whim. You're serving that criterion as the master. And in some sense, you may say, I don't really need that. But their goal is to really screw you up. That's why they're there. They're there to screw you up. And when you submit a patent, they're going to say, I'm going to get an airtight case against you and make an office action that you cannot appeal because I don't want to see an appeal. I don't want an appeal. And if there is an appeal and I lose, it looks bad on me. So your patent examiner has been trained to create an airtight case for a prima facie argument that you have trivial patent. Obvious based on prior art. Okay, I've chit-chatted long enough. Let's stop this and let's get back to student presentations. What I'm going to do is I'm going to stop this Cam Studio recording. We'll take a little break and I'm going to download your homework assignments so that you can do your presentations. So let's do that. Okay, we're back. I thought what I'd do is go in order like we usually do, getting the PowerPoints from each one of the students in turn. I guess we're missing George's. I know he's sick. Let's see what we can do here. Alfredo is going first. Now this is supposed to be about the references, right? Just references. This is looking huge. What are we looking at here? Alright, well, let's let it run.
Quality Flow, Active Noise Cancellation by Alfredo Torres. Paper 1. Silent Night and Silent Days. This paper explains how the size of blowers can generate sufficient airflow and do much noise. The difference between my work and the prior work is that I use a small fan instead of blowers inside air conditioners or compressors. Paper 2. Active cancellation system and acoustic noise in NR images. Paper is about active noise control, where it is employed to suppress acoustic noise. There are two types of ANC algorithms: feed-forward control and feedback control. The prior work coming to design for feed-forward control logarithm. My design uses two microphones in order to estimate source location and speaker position. Paper 3. Modeling, identification, and feedback control of noise in an acoustic conduit. This paper considers a single input, single output plan involving one control actuator and one control sensor. Additional speakers and microphones are used to provide disturbances and to access closed-loop performance. My word is different because my control sensor is going to be closed loop and this loop is going to be connected to the overall loop in order to improve performance. Paper 4. Down with Noise. This paper talks about measuring the acoustic energy. This energy should require an infinite number of microphones, since the energy is proportional to the volume integral of the mean square pressure throughout the enclosure. My work is designed for low frequencies. The prior work focused in a wider range of frequencies. Paper 5. Active Noise Control, a tutorial review. This paper is about the development of ANC. The improvement of this device permits improvements in noise control, size, weight, volume, and cost. The ANC system that I am going to have must be adaptive in order to cope with variations. Paper 6. Active Noise Control. This paper is about active control of low-frequency plane waves propagated in ducts. The microphone has to place close to a loudspeaker, acting as a secondary source. My word is different to the previous word because my speakers are not going to be close to the microphone. Paper 7. Active Noise Control for Periodic Disturbances. This paper proposes an active noise control algorithm for periodic disturbances on unknown frequency. The application of the algorithm is for a feedback case in which a single error microphone is used. My word is different with the prior word because two microphones will improve noise reduction. Microphone 1 is placed close to the source and microphone 2 will be placed after the loudspeaker. Paper 8. Active Control of Sound and Vibration. This paper is about the active sound and vibration control field. Active sound and vibration control has found use in the 50 to 1000 Hz range. The difference between my work and the prior work is that the vibration that is produced is low. Paper 9. One-dimensional acoustic duct using a feedback controller. This paper is about active noise control of one-dimensional hard-water duct with a partially dissipative boundary condition. The work presented applies to reduce noise levels in one-dimensional acoustic enclosure rather than at a single location. My design consists of 6 speakers inside the muffler in order to be more efficient. The text in the prior work used 1 speaker. Paper 10. Constrain Filter X and Filter U least mean square algorithms for the active control of noise in ducts. This paper discusses the acoustic error path. In the active control of noise in ducts, it is important to locate an error microphone far from the control source to avoid near-field effects by evanescent waves. The prior work is different to my work in the location of the error microphone because I don't use least mean square algorithms. Paper 11. Active Control of Sound. This paper explains the idea that noise might be reduced by machine-made. The most important thing in this paper is that sound is a pressure variation linearly related throughout space and time to prescribe source activity and boundary conditions. My work is different to prior work because space and time in a small conduit is going to require more calculations. Literature cited. Thank you.
So one thing I noticed about the literature cited at the end is that if you were going to do something like cherry, you'd write cherry, and then you would cite cherry somewhere else in the paper. So you'd have to put it in brackets or you'd have to number it and then cite it by number. If you use the IEEE format, you use numbers. If you use the ACM format, you use the angle brackets. It's my preference that you use the angle, the square brackets, because that just makes it a little bit easier than having to renumber things all the time whenever you insert a reference. So I would say something like this: if Elliot is here twice but has 2 different dates, then I would do Elliot 1999 versus Elliot 1993, just so that I could know that the two references are different. And that's how I would cite them. Is Hull in there twice? No. Okay. I don't see any other duplicates. Now, are there any questions about this? If you see something like this, that AL is an abbreviation. It's AL-E. So put in a period. That's typical. You know, that's a normal error to see. So if you see et al, put the period after the al, but not after the et. Et al-E means and others in Latin. In something like this, I would just say Eliot 93. That's sufficient. Then you could go back down to the literature cited. Because otherwise what happens is this takes up too much space in the body of the text. I know it seems like a minor point, and maybe it is, but in effect it'll help you later, because if you can get it right to begin with, you don't have to change it later. It'll also make the text tighter. So this could have just been Eliot 96, that would have been sufficient. But clearly, if you were going to write something like Eliot 96, you would want to look for that in your literature cited. So somewhere, there should be an Eliot 96. Now guess what? I'm not seeing it. I see Eliot 99. I see Hong 96. I see Eliot 93, but I don't see an Eliot 96. So that's a problem. We've got a bug in the citation. Either I got the wrong date or we missed out on one of the citations. I'll look for that. -5. No, just kidding. No. But yeah, you can pretty much say that you should be consistent with your literature cited. And this is one way in which you can do it, by citing it properly. Then you know if you've made a mistake. Okay. It's Sarisha and the dry ice superconducting motor. Did you see the video on the homopolar motor I sent you? That was fun, wasn't it? Well, you wanted to do a superconducting homopolar motor, didn't you? And we said, hey, what's a homopolar motor? And you didn't know. So I had to go look it up. It's a good motor, though. I thought it was very fun. I tried to build it at home. It didn't work at all. So I ordered niobium magnets because I thought I needed more powerful magnets, because I wanted to build the motor they showed in the video. I don't know if we can see it here because of our network, but I just thought it was very fun. We could try and find it, I suppose. Google. It was fun. Homopolar motor. Yeah, there they are. You can just take a piece of wire with a niobium magnet and the wire is balanced on top of the D cell. There's a niobium magnet on the bottom, and this whole thing spins around. And it just goes on its own. It's kind of a really trivial thing. You get a magnet, you get some wire, and you set it up, and then it just starts to spin. Oh, do you think maybe this will play? I never know what's going to play around here. I think the niobium magnet is very important. Now, if I buy you some dry ice, will you be able to make your dry ice motor work this way? Because I think this is a very fun thing. Can't you make the wire dry ice high temperature semiconductor, a superconductor, and then when you put it on your magnet, will it? Well, no. I mean, it should work at dry ice temperatures. There is wire that works at dry ice. I want to build this motor with your idea about using superconducting wire, and I have a feeling we can probably do it with very little extra expense. We should just do it. I think it should be done. Well, anyway, I want to build the homopolar motor. Obviously, it can be done. That's easy. And then, or it looks easy, but when I try it at home, it doesn't work because I don't have the right magnets. But I think this is cool. You gotta get me one of them. Okay, so sorry I took your time, but you can still talk. Okay, you're up. That's a fun video, wasn't that fun? Very fun. I like that. I never saw one like that before. It was very interesting.
Okay, I'm going to present the papers that I have read with literature cited. This is the first one. This is the regarding materials, superconducting materials that works at that exhibit superconductivity at high temperatures. This paper describes shows the properties of that material, which combines, like if we combine some chemical products, it exhibits superconducting. One of the conductor is bismuth, plumum, strontium, calcium. It's a formula for that, like not the formula. It's a chemical molecular thing.
How do you pronounce that chemical? So that's bismuth and lead.
Yeah.
Tin and
Strontium, calcium, copper, oxide.
Strontium,
Strontium.
calcium, copper, and oxygen. And what is the name of this compound?
They didn't mention.
Oh.
Yeah, they just mentioned that formula for it. So and the other one is like how this superconductivity is applied to motors. If we have a superconductor which exhibits superconductivity, we can make a magnet with the superconducting wires. So we can use that magnet in the rotor of the motor, so that we can use that in electrical motors.
So let me ask you another question. Can you make a superconducting magnet without using superconducting wires? Can't you just have like a permanent magnet that works at superconducting at high temperatures, like dry ice temperatures?
I mean, if you have a material, we can if we can make that to exhibit superconductivity at that temperatures.
So okay. Suppose I took a niobium magnet and it's working very well. I think I have one here actually. I found some niobium magnets. They're part of this thing they give us, the name tag. So here's some small niobium magnets.
Okay.
And now, if I take these magnets and I put them in the dry ice, will they still work, or will they lose their magnetism?
They lose their magnetism.
So
they don't
lose it when it gets cold.
Yeah.
That's not good.
Yeah, we need to have the material that works at dry ice temperatures.
Yes, you need special magnets.
And this comes homopolar motor. I have read this one because this use superconductors, so I can have an idea how to use superconductors in motors and how to implement those. This homopolar motor is basically a motor which works in, like, it has two poles. It works with direct current. So it rotates like one pole is rotated and the magnetic field is pushed to the other pole, and then it rotates. It's two kind of poles in there. So they use superconducting field windings in rotor for this paper, and then they use bismuth 2223 as a superconducting material. Bismuth 2223 is also exhibits superconductivity at high temperature. In these papers they mention high temperatures because they work at liquid nitrogen temperatures.
So when they say high temperature, they mean liquid nitrogen temperature.
Mm.
They don't mean CO2
The-
temperature.
No,
But you can have a CO2 temperature motor too, right?
you can have it like if we. This one is like they use the homopolar motor in navy applications. Uh, Basically, the advantage of superconducting motors is like they decrease the size of the motor. So they decrease the size of the motor and they increase the efficiency of the motor. So they use that one in the navy application, and they use like copper brushes before that, and then before that they use liquid metal brushes like to clean up the rotor things, rotor windings. Before they use liquid metal current collectors, and in this homopolar motor for propulsions they use copper brushes to clean those. So it has very advantages compared to the previous homopolar motors. So this one also superconducting permanent magnet model. Permanent magnet is like rare earth, made of rare earth materials. Neodymium is one of those, and they made. I mean, they designed one of these superconducting permanent magnet motors, and then they use direct control algorithms. Direct control algorithm is like they prepare some equations based on the direct control method. They use that equations to get the torque and torque characteristics. Based on those equations, they use the material that we use in the stator windings.
So Suresh, I'm thinking that you need to like put in the little square brackets in the future and make sure you've got the authors listed.
Yeah, I have written
Well, I mean,
in
when you do the citation, it can't just be called paper 6.
oh.
It should have like a proper citation with the square brackets and the author name.
If it is paper 6, I mentioned 6 and then put in the brackets at the end.
Yeah, but then I have to go numbering papers. See, you see where you have your brackets? You just want to have like edict and then a square bracket, and then
Oh, I need to put this one over there.
yeah, you want to cite it properly.
Or just I can mention from reference to, like
Beg your pardon?
or like I can mention like just from reference to or reference 1.
Yeah, if you just do reference 1 and reference 2, it doesn't speak to the author or the title of the paper. So what you really want to do, I think, is just say edict or edict 92, and then we know that we can go and see here. If these references are in order, their order it would be alphabetical, not numerical.
Oh,
That's what I'm thinking.
okay, I'll do that. This one is with like they use magnets that exhibit superconductivity. This one is the material that at uh, yttrium, barium, copper oxide. This one is the material that used to that works at high temperatures, means 77 K.
So these are the CO2 superconductors.
No,
No?
no,
Only liquid nitrogen.
liquid nitrogen.
Okay. I get confused when you say high temperature.
Sem,
You mean low temperature?
Previous papers are like everything they made with liquid nitrogen temperature. I haven't get any.
Well, I mean, these guys are saying 30 K.
They are cooling that bulk magnets at 30 K.
30K is very low temperature. That's 30 degrees Kelvin.
Yeah.
So that's like minus 240 degrees Fahrenheit or centigrade. That's
They're cooling those magnets in the refrigerator.
30K. That's not, they call that high temperature?
These magnets exhibit superconductivity at high temperature and they are cooled down by 30 K.
Or they're cooled down to around 30K, or they cooled by 30K.
Around.
Around 30K. Minus 240 degrees C. That's very cold. And liquid nitrogen isn't that cold. I thought it was quite a bit warmer.
Yeah, these magnets, yttrium bulk magnets, they exhibit that superconductivity at that temperature.
I see.
And these are the superconducting motors uh, that that are used in naval applications. In Navy applications, superconducting motors are very interested in Navy applications because they reduce this ship's motor size so that they can reduce this ship size. So they use those superconducting magnets at liquid nitrogen temperatures in the rotor field magnets, and then they use that one in the ship. They designed that one. This one is this motor like they use to superconducting field windings in stator, not in rotor. In rotor they use just regular magnets, permanent magnets, and then they in the motor, like stator windings, they use superconducting high temperature superconducting windings. So it's different from the other papers. Like we can do stator windings with superconducting material, or we can do with rotor windings also.
And what's a GM cooler?
It's one type of coolers like that are available in.
And what does it stand for?
It's I look for it.
If you don't know, that's okay.
I noted
Find
one.
another video.
I noted down that one, like GM. I look for it when I see this. What is GM coolers? And I look for it. So like this one is axial type, one of the superconductors that exhibit properties at high temperatures. So this one, like they use boron, strontium, calcium carbonate. They use mostly boron, strontium, calcium carbonate oxide material in superconducting magnets for getting high temperatures. So they just studied about these ones, and then they made the torque speed characteristics, and then and they showed the difference between the previous studies and this one with the boron, strontium, calcium carbonate, copper oxide material, why they are using the benefits of that material and everything. So this one is like, if we use high temperature superconducting linear synchronous motor, that means we use superconducting motor in linear synchronous superconducting magnets in linear synchronous motor, and because of using these magnets we can increase the electromagnetic performance, because it superconducting materials don't have the resistance, like they just exhibit the magnetic properties in the rotor windings. They don't have resistance. That's why these are important. So its electromagnetic performance is increased. They designed that one, and then they showed that this in this. This one is this one shows the characteristic analysis of the superconducting synchronous motors with like with the high temperature superconductors that are used in rotor windings.
What was LSM stand for?
Linear synchronous motor.
Tell me again, what is a linear synchronous motor?
Linear synchronous motor is like it when like when we have the motor operation in rotor, so it operates with the different poles, right? So it gets the other pole to in the field of the magnetism.
So it has a stator.
Yeah. So this paper discuss about the bulk magnets that I mean how to like why you are using bulk magnets that exhibit superconductivity in the rotor windings and all. So and then if we use different sizes of the bulk materials of high temperature superconductors, we can have the different analysis results, and then they compare those results in like by using finite element method. And this paper describes about the high temperature superconductor motor with different temperatures, but how this material that bismuth 2223 is working, like they exhibit different temperature conditions, and then how these they explain how this is how the motor is working under different temperature conditions. This one I didn't find out the paper for this because like the they didn't provide me like this one is on IEEE. I placed a request with the library, but they didn't respond for this paper. I ordered it 2 days back, but they didn't respond it.
2 days.
2 days back.
It takes longer than 2 days to get
Yeah, I found it 2 days back, this paper, so I didn't get the response. So but with the abstract I found, I got some like and the George told like explained with Maglev systems and all, so I got an idea, brief idea about this. They use magnetic suspension subsystems in the motor, high temperature high temperature superconducting magnetic suspension systems to create this superconducting winding. So we can use those motors in emails, maglev, and they use those
Here
ones.
thinking about it would be a railgun. It shoots airplanes. Right? Give them a boost.
Yeah, I think so. And then we are looking for the superconducting motor at driest that works at driest temperature. So we need to have the material magnets first in the that works in at driest temperature, that we need to look for it first. To have a magnet, we need to have superconducting wire to
It has to be an electromagnet. You can have a permanent. Can't you have a permanent magnet work at 195 degrees Kelvin? No?
no.
Do they all lose their magnetism?
Yes. So like if
You mean if I go out to the store and buy some dry ice and throw my little niobium magnets in there, the paper clips won't stick to them anymore?
I guess I'm sure about it, but I haven't tried it.
You can try it.
Okay. Just let me know.
If it works, so it will be reflected in your grade.
So if we have a superconducting magnet, we can have the motor. So first I was thinking like if we have the magnet, so just first to prepare magnet, how to prepare magnet. if we have superconducting wire that exhibit the superconductivity at driest temperatures, we can have the magnet. So superconducting wires are like prepared from the materials that exhibit the properties of superconductivity at driest temperature. So when I search for it and you send me some links, I have seen those before, but I haven't looked those briefly because do they really exhibit superconductivity? I mean, do they or like to make magnets, or I haven't looked at. When I look those, we have a material that exhibits superconductivity properties. That material is this uh, whatever is like uh, a plumbum, indium, that this one barium. So with this one is like 1256 by 1212 structure. So we already have those. We have 1223 1212 structure that exhibit superconductivity at 163, and then they had the research, and then they found out that this material exhibits superconductivity at 195K even. So if we use this material to make superconducting wire, maybe we can.
Can't you just go out and buy wire that's made of this material?
I think we don't have this wire. Like when I look this one, like it has this process, uh, sintering process. I think we can make it.
I can't make wire. I think making wire is hard. I want to buy wire. I can't just buy this material.
I need to look that
I
one
want to go
because
to a
it's if
superconductor
it is
store and
available
just buy
in
it.
market, I would like to buy
Maybe on
it.
eBay. Yeah, let's buy it. Never build what you can buy.
Yeah, if we have a wire of this material, we can have the magnet with this wire, and then we can build motor.
So we need to buy some high temperature superconducting material and build our superconducting homopolar motor. I think it's important. I'm going to finish the thesis.
These are the literature cited.
Who's up next? Spurti.
Today I'm going to tell about a prayer paper list, and this is the first one. And in this one, in this paper, they mentioned about the wireless power controlled output module, which has a AC power sockets, and they have a low power microcontroller, which controls the switches to be on and off at the sockets at the power outlets. And then they have 6 scalable modules into power outlet, so that they can control any device from outside, and they can make it on and off and measure the power, and this is very easy. They just need to set it up. They can get an switch, the low power microcontroller, and then they need these modules to find out those. And this is a citation of this paper. I mentioned that in the last also, but I just wanted to mention it in each and every slide. And this is the path of the smart grid, and this mainly explains us how smart grid is evolved and how it works and how it is helpful for the society. And then it has how it explains about smart meters, and it explains the way we can use smart meters so that we can know how each smart appliance is measured, each smart appliance power is measured. And then it will also have so many drawbacks like the privacy, and it explains everything about the smart grid. This is the third one, and um, in this one the paper is mainly concentrated on smart meters, and in this one it just tells us how smart meter power is measured in the smart meter, and how we can know the whole it will measure up to 2 months of the all the details of the home. That means when we are using more power and everything, so that when we have 2 months details, it is the privacy is not there, so that they know how many people are in there and how much everything is using. So this is the main drawback of smart meter. They explain this in this one, in this paper. And in this one they explained about the we have a transmitter and we have a receiver. Near the transmitter they want to encrypt the code, all the signals, so that they can get secure information. And they have a different route also, so that exactly how much power is measured without any hacking or everything, so that if the other guy is also using the same RF signal, so that because of this encryption we can get a exact measurement of the one which he is using, not the other person.
Tell us what homomorphic means.
Homomorphic, it is it is a different way to encrypt all the signals and everything. I
Tell
don't.
us what isomorphic means.
I have no idea what.
Isomorphic means 1 to 1.
So this may be from one to different.
I don't know.
I'll read more about it.
Yeah, I think if you're going to use these words,
Okay.
you have to know what they mean.
Yeah.
Let's not use big impressive words without being big and impressive.
Okay. And this one, they try to use advanced metering infrastructure, and this tells us how we can use a Zigbee communication for the transmission of all the signals. And this is integrated into the meter, and then it transmits the power consumption at the and it is received at the rear end processing. It is received at the main control power hub. And this one we have it right now in the market and they're using it. This one is a kilowatt, but it is a wireless sensor of a kilowatt. We have two things in the market: kilowatt, which we have to note down all the signals, and we have one more thing. It is a new one. It is a wireless measurement of the power, so that no need to note all the signals. It will automatically note all the signals, and it will give us the power consumption. And
How much is Wattbot?
sorry,
How much is Wattbot?
it is just a name of the system.
Oh, can I buy it?
Yeah, you can. I think so. Yeah.
So,
They mentioned that in the paper that they're trying to find this one, but the appliance which they are using with this Wattbot, it's like the name of this one, this system. The one which is in the market is a kilowatt, the wireless sensor.
well, I own Kilowatt. But Kilowatt is not a wireless sensor.
We have one more thing. The same name is as kilowatt, and it is a wireless.
New.
It's a new, yeah, yeah. And even with this we can get all the readings into a web portal or iPhone. Even we can see all the data. And this is little related to my idea. It means this one they wanted to know how people use energy consuming products, like without knowing, without realizing they depend on energy so much. So they just wanted to with this paper they wanted to explain that people are depending on the electrical and energy power, and they have to know how much they're using every day. And because of this they explained about how to measure the power consumption and everything. And this one, they have an automatic meter reading system, which is this is a remote reading which is used to measure power. And then in this one they have different meters, and they have nodes, and all the nodes they collect the data and they'll send it to the main server. And this is all, the whole thing is wireless, so that they can get all the details by using this technology. And in this one, the users will have the ability to control any appliance through internet. Like they can sit here and they can just activate the device and anything with the help of Bluetooth and wireless. And they can even switch it on and off, and they can know the power of each device, how much it is consuming. And this one, automatic power meter reading system, I think this is used right now in the electric grid. I have no idea about it, but I think they're using this. So whenever we can see the UI bill, we can see the how much data we are using every day and at what times we are using how much. And I don't know about the SMS thing, but web portal we can see how much we can expect this month and how much energy we are using each day and at what times we are using the maximum energy. And with the help of this network, with the automatic power meter reading, they are using this.
What does GSM stand for?
Global System Module. And in this one, we don't know how much power we are using, and there are very less renewable sources, and so the residential, so very less renewable sources, so they just wanted to save all the power, and they wanted to know how much each residence is consuming. So in this paper they explained about the increasing electricity prices and why we need why we need to see how much power we are using and how we need to save the power. And this helps us in the and this paper tells us exactly how about devices which we can monitor the power, and then which we can use. And these are the papers citations. The one thing I didn't do was at all, I didn't put a period, I didn't know about it. So, and
Well, also, whenever you made a citation, it didn't seem like you related it to your contribution. So we want to try and identify why your stuff is different
different.
from what's been done.
You want me to tell it here now from each paper?
Well, no, I mean, you can certainly, if you have some.
Yeah.
What is your contribution?
Like I wanted to find I wanted, like, not exactly, but want to find the power which is consumed by each electronic device, so that we know how much each electronic appliance is using, like by at the outlet. Because we have the smart meters, they have smart appliances, they're trying to make the whole appliance as a smart. Instead of that, I just wanted to use it at the outlet.
Well, isn't that what the wireless web-enabled outlet is for?
Which one?
The prior that.
This one?
Yeah, who's web-enabled outlets? Isn't that what that's for?
I think in this one it just tells us in my thing I'm trying to from each outlet it is the whole reading is sent to the main server, so that each and every appliance how much is using, we can just note down all the details.
So why is that different from this?
This one it just tells us how much each device is using, and it doesn't note down all the things at the center, like
Maybe it monitors it, but it doesn't write it down?
Yeah, it
Your
monitors it.
contribution is you write it down?
not exactly write it down. I'm not sure about it. I told you, like, before I didn't know that there were so many products in the market, so
So
yeah,
you don't know your contribution yet.
yep. That's it. These are all the papers which I assume they are related. That's it. I didn't know that there were so many products out there. Yep. And a little difference to my and those, so I don't think it has a contribution.
Yeah, I need to know, you need to know your contribution.
Yeah.
Thank you. Okay, who's next? Shitan. Um, can we take a little break? Let's take a short break. Shitan, you're up.
Hi everyone. My my presentation is about maximum power point tracking. This is the first paper, standard and adaptive techniques for maximizing energy capture. Uh, Basically, the operation of turbines have divided into three regions: region 1, region 2, region 3, and this paper is mainly focused on region 2. Region 2 is something is getting maximum energy at low speeds or moderate speeds. And in this region, there is a control unit called General Torque Control Unit, and this control unit in this article, this control unit is stable, is made adaptive and it's made undergone a stability analysis. It's like adaptive is something like you give some certain set of values where it should operate. It's like if it is the turbine is operating in a reverse direction, you don't get particular output. I mean, I'm trying to explain what adaptive is. This is what explains in this paper. And the second paper is a method of tracking peak power points for the variable speed wind energy conversion systems. In this paper, it's normally induction generators are run at synchronous speeds only because the starter is connected to the grid mains. That's the reason they are run at synchronous speeds to get a particular frequency. So this article provides a solution for that. It introduces two blocks between the generator and the grid, so that it's to bring up the system to a variable speed and constant frequency system.
I have a basic question.
Sure.
So, is it the case that all these generators are AC generators, not DC generators?
Some generators are AC, some are generators are
Well, if
DC.
they're DC generators, why do we care if they're synchronous?
I mean, for this paper, they took on the AC generators.
So you're assuming, the assumption here is that we're dealing with
AC generators.
and you want a frequency that is in phase with the frequency on the main.
Yeah, that's the reason they are operated in synchronous speeds. And with this, so in variable speeds, we are not gaining the additional energy, and that's the reason this algorithm is introduced to maintain the system as variable speed and constant frequency system. And the third paper is double feed induction generator systems for wind turbines. Here in this paper, it explains adjustable speed generators and direct line adjustable speed generators. It introduces a solution for this, which is cost effective and improves the efficiency of the system, but with a double feed induction generator, which is like rectifying, like inverter thing. It uses IGBT, like I mean, what's that? Transistors, bipolar transistors, insulated bipolar transistors for this inverters. And the other paper is design of maximum power point system for wind energy conversion applications. Here, usually the output power is calculated with the output voltage and current, and by adjusting the duty cycle, with the in DC converter, we'll get a constant. The power is grabbed. It's like they convert the complete AC to a DC, so that there is no point discussing of frequency, but the complete power is captured, and then it's used for usage. I mean, if it's a DC, it's okay, and if it's AC, you need to convert that. And the next paper is MPPT, control of wind generation systems based on estimated wind speed using SVR. SVR is a technique of sport vector ignition. It's like the variables have a couple of algorithms. With the given inputs, it estimates which algorithm should run or which to get the efficient output. This is what SVR means. And for the SVR estimator, the rotational speed and turbine output power is given as the estimator to run the required power characteristic pattern or for maximum. The next paper is development of microcontroller based photovoltaic MPPT. In this method, a buck type DDC converter is used. This here microcontroller unit is used, which is taking an output power from output power. This comes under power signal feedback. I'll explain you what actually PSF control methods are. Basically, there are three type of control methods in turbine systems. First one is PSF, power signal feedback, and the other one is HCS, hill climbing searching, and the other is TSR, which my idea is about, which I'm working on.
What does TSR stand for?
Tip speed ratio. And
So your idea is different from power signal feedback because your idea is not using a buck boost converter
no,
to try and create the DC level of the mains. So your idea is to try and do synchronization by controlling the tip of the rotor.
yeah,
And so you do that by adjusting the pitch of the blade.
yeah, pitch of the blade, and actually it's like a control unit which is moving between TSR mode and hysteresis mode.
So how come nobody else uses this technique?
I don't know. I mean,
Is it because you're brilliant?
no, it's not. I mean,
You must be brilliant. You thought of it, no one else thought of it.
no. I mean, I found this is something like used in photovoltaic cells and hydro generation projects, which are run
So
with
others have
hysteresis.
used it, but just for other applications.
Yeah. So there's no one used hysteresis in this wind generation.
Very interesting.
Um,
So you built a better windmill. Maybe.
and the other paper is intelligent maximum power point extraction algorithm from inverter based variable speed wind turbine systems. And as I told you, it's HCS, hill climb searching. It's something like with the wind speed which we take from the anemometer, it compared with the maximum power. So it's like the power will be rising compared to the wind speed. It's called hill climb searching control method, and here an intelligent memory is used to implement this hill climbing searching method, control method. And the other paper, it's pitch control variable speed wind turbine generation. This is for in low turbine and low and moderate wind speeds. It just works to get maximum energy, and at high speeds, these are the two control methods used to control the aerodynamic power. One is pitch control method, and the other is generator load control methods. This is what was discussed in this paper. Pitch control is by stepping pitch size, and control load is the load of the turbine is varied, so that to get at high speed wind speeds you get power. And the other paper is a novel algorithm for fast efficient speeds and so that. In this, as I discussed in the previous paper, this is about hill climb searching, where an adaptive step size is chosen to for the rapid wind changes. The other paper is comparative study of maximum power point tracking for photovoltaic cells. In this method, the MPPT calculation is focused on frequency modulation scheme, switching frequency modulation scheme. This is done by comparing the AC component and the threshold level, terminal voltage of the solar panel with an injection of small sinusoidal wave. It's comparing all the three. These are some citations I found.
So it seems like we need a kind of a taxonomy to organize the
Yeah.
various papers.
Yeah.
What do you suppose would be a good taxonomy to these papers? If you told me there were two kinds of control systems, those that dealt with DC and those that dealt with
AC.
that might be a reasonable way to go.
Yeah, and under AC, like rectification and in so under AC it's like rectification and inverter control, and under rectification.
That I would have said that, and maybe this is not right, but my guess is that there are controllers that are mechanical
Yeah,
and those which are
electrical.
And you could have said, instead of AC and DC, you could have said mechanical versus electrical
Yeah,
for regulation. And if you did it mechanical versus electrical, then yours would be sorely in the mechanical case.
mechanical.
And the electrical guys, it would be very easy to say, well, here are their contributions, and there are AC and DC within the electrical community. And then you can say, but mine is different because I'm in the mechanical community. And then when you compare your papers, it's very clear that you need to compare your papers on the mechanical side. Because there may be other papers that deal with mechanical synchronization techniques. If there aren't, then yours will be the first.
I searched these papers with I thought to get idea what are the control methods and what are the efficiency improvement methods that are implementing right now in turbine systems. And these are the papers I found.
Which mechanical techniques work might be to use a motor and a generator. And the motor-generator combination, that can be controlled directly. So if you have a motor and a generator, the generator could be AC, the motor could be DC, and then you've got a DC to AC converter. And if you look at, for example, the basement of Grand Central Terminal, they have a high voltage DC system. And so they need AC DC converters, and they were actually done with motor generators, because in those days, when they created it 100 years ago, they didn't have electronic means of converting easily and efficiently between AC and DC. So to do it, they needed a motor generator combination. So you can achieve, I'll say, not electronic, but electric conversion, right? Because if you think about it, electronics would require semiconductors, but electrics, where you have a motor and a generator, that's not quite electronic, and it's not quite mechanical either. So it's both electric and mechanical. So it's an electronic. It's an electric converter, but not an electronic converter.
Yeah.
So it's just like a relay. You but it's not an electronic switch like a transistor.
Transistor.
So maybe there are these mechanical contrivances that aren't purely mechanical. So if I have the taxonomy, I have electronic, and I have electromechanical. And then within the electromechanical, I have purely mechanical, and then I have purely electric. But even when you vary the wind speed, that almost seems electromechanical. That does seem like you've got an electrical device there.
Yeah.
So maybe it's electronic versus electric.
Yeah.
Because the electric always refers to electromechanical. But you could just call it electromechanical and describe all the electromechanical interfaces that are available. That's very good. Thanks. Did we do everybody? I guess we did. Oh, cool.
Yes, of course.
I want to tell you a little bit about my adventure with Freelancer.com. Freelancer.com allows you to find low-cost professionals in a variety of places, and they can do things to help with your project. And one of the things I wanted is I wanted to find a freelancer who could help me to script code in Eagle using the Eagle scripting language to create a fractal inductor. So I put out a bid to see if anybody would be willing to help us, because I have a feeling that, Raul, you are not an expert at Eagle. And I know I am no expert either. So what I did was I created an offer to pay for a job, and I thought that the project, let's see, my projects, the project shouldn't cost too much, because I don't like to pay too much money for these things. And let's see now, if we look at it's a little slow, isn't it? Here we go. Let's look at the Eagle scripting for printed circuit board design. You can see the range of prices. The average bid is $1,500. I feel hopelessly middle class because I said you can spend between $30 and $250. Someone thought, oh, wouldn't it be a kick if we budgeted $10,000? I said, thanks a lot, buddy. And I specifically don't like it when I said, do not bid higher than the maximum price of the project. Right? This is what I wrote. And apparently somebody has like trouble reading English and understanding, because when you look at what they bid, you see $10,000. Right? Now, who does that? Ridiculous. Really ridiculous. Do not bid higher than it says. It's silliness. Some silliness. So then I said, well, and Raul, of course, you know, I have your mind in mind. Right? I wondered, can we get somebody to do a wireless power transfer based in fractal antennas? I don't want them to make this. I just want them to write the code so that we can see it. You know, and this is not a bad way to go, because if you can find somebody who can work for cheap to do something that you don't have good skills in, you can basically, it's like paying tuition. You're going to Eagle scripting class. You know, this is like paying a good plumber to fix your leak and then sitting there and watching them so that next time you don't have to pay them. You're basically going to the school of hard knocks by paying someone who's excellent at this, and then they show you how it's done, and then you can say, aha, now I know. So I gave them this idea of this paper, and this is, I'm trying to do the Sierpinski fractal antenna, and I said, you know, do not do not bid higher than maximum price. And so the bids are all over the place. 220, 100, here's $35. I think that's pretty good. For $35, if I can get somebody to actually do some good work, that would be great. So I awarded him the project, and then he ignored my award. I mean, really ignored it, which is kind of unfortunate. And then I thought, well, we'll look at some of these others. But before I go on, I would say, gee, wouldn't it be fun if we could find somebody who could actually just do a quick prototype for us, and then we could send it out to batch PCB and see what happens. I think it would be a good time. So if you're thinking in terms of getting a project jump started quickly, this is a way to go. Prototypes can be had this way. And me, I don't have enough time to do all the different projects for all the different students. But maybe there's a little money available. If it's $35, I don't care. If it's $220, I say no. I can't do it. It's not unless you really want to do the thesis. Then maybe we could do it. We can budget. So I just thought I'd point that out. These things are possible, and the people who bid are everywhere. They're in all these. This person is in the U.S. Oh no, he doesn't say he's in the U.S. He's from India. This person is from Turkey. This person is from Romania. This person is from Colombia. This person is from the UK. This person is from Pakistan. And here's somebody from Israel. It's a truly international collection, right? A world team of individuals, all expert at Eagle. Isn't that interesting? And we can find them efficiently through Freelancer. It costs nothing to post the project. They charge you extra over and above what you award, and that's how they make their money. So if it's a $35 award, they probably take about 10% right off the top, $3.50 just for them, because they made the match. But if you don't make an award, there's no charge. So you post the projects for free, and you can see where the bidding comes in. Sometimes it's very good if you could find somebody with a good reputation, like this person. But when you're looking at the reputation, if it comes at a cost, then you have to think, oh dear, you're really paying up for that. Maybe it's worth it, and maybe it isn't. So I thought I'd just point that out. I did this, had your mind in mind. Okay, so if you get serious with this thing, we can go with some of these bidders.
Good afternoon, everyone. My topic is Vitricity using fractal antennas. So the first paper is not so original after all. So this is the basic idea of the Tesla, which uses an induction coupling principle to transfer the power wirelessly. So some of the people in the MIT had done this, but there was a restriction in the experiment, that is the limited distance. And the next paper is Goodbye Wires. So there were 6 people in the MIT who did an experiment, who practically used the concepts of the Tesla and made a live example of the power transmission wirelessly. So it was potentially useful for powering laptops, cell phones without cords. It is that when the equipment is brought into a range of the source, it gets charged automatically. It doesn't need any battery or any kind of device when it is in the range of the source. And the next paper is Wireless Energy Transfer for Refrigerator. This was actually patented. So there were some improved configurations because the refrigerator generally uses more power. It operates in a different frequency with different current input and output. So there were some modified configurations that they did for the using the Tesla concepts, and they were successful powering up the refrigerators. And the next paper is wireless energy transfer using magnetic materials to shape field and reduce loss. So there was another factor that uh, that is a major backdrop. So that was to to range the um, to range the area with which the source is offering, and also there is a loss while the energy is being transferred from the source to the destination. So this paper solves the problem using some magnetic materials. It shapes the field and also reduces the loss when the power is transferred wirelessly. And this is the fractal antennas, a novel antenna miniaturizing technique and applications. So the term fractal means broken or irregular fragments to describe a family of complex shapes that possess an inherent self-similarity in their geometrical structure. So here this fractal is like it helps within it a self-similar design to maximize the length and increase the perimeter of a material that can receive or transmit electromagnetic radiation within a given total surface area or a volume or a region. So what I was thinking, why don't we, because the vitricity concept is a limited distance, it was limited with a restriction, so why don't we use the fractal antennas to maximize the length and increase the perimeter of the region for achieving good efficiency, and also to minimize the size of the antenna, which is like very useful product. And the next paper is an iterative model for fractal antennas. Here this paper mainly deals with the experimental and numerical methods, which show that the self-similar properties of the antenna are translated. How the properties are translated into an electromagnetic behavior, which we can use in the vitricity concept to transfer the power wirelessly. And the next one is frequency independent features of self-similar fractal antennas. So this self-similar property is also shared by many fractals. The main thing between this vitricity using the copper coils and the fractal antennas is when we use the copper coils, we generally operate them with a frequency of in a range of the radio frequency, which is 3 kilohertz to 300 gigahertz. But this fractal antennas, that they operate at 6 kilohertz to 600 megahertz. The frequency is like limited, but still I think we can use this because it has the property of maximizing the perimeter and the region. So but still I think we can use this fractal antenna concept to extend the area of the source.
So right now people use vitricity without fractals.
No,
They
there
use
are
loop, right?
copper coils.
Just the copper coil. What frequency do they use in the coil?
They usually operate at the radio frequency
Well, that's radio frequency?
the radio frequency. But this fractal antenna actually operates in in the middle, like from 6 kilohertz to 600 megahertz. There isn't that wide range of the radio frequencies.
Why is that?
It's the property of the fractal antenna that it operates at that frequencies.
Yeah, why does it have that property? You know?
No.
Does anybody know, do you think? Maybe it's just a mystery.
Because I had read so many papers with the fractal antenna, even the Wikipedia, but there is no.
There's a lot of corners. There's a lot of edges.
Yes.
And if you go down deep, you're making microstrip arrays. It seems looks like every edge would be another transmission line.
Yes, at every particular, that is what the fractal means basically, right? So at every edge we can transmit the electromagnetic radiation. We can use the self-similar property of the fractal antenna, and we can transmit the
So
electromagnetic
it doesn't work
radiation.
at all at low frequencies, like 0 hertz.
No. It's a disadvantage, but most of the products usually work within this frequency range, so we can use the fractal
But
antenna
if
to
I
power
want to run it at 60 hertz, like an AC line, that wouldn't work either. It's got to be more like
60
6
hertz. Yes,
kilohertz.
yes. But the vitricity can be used with what the Tesla had came up,
Yeah,
so we
that
can,
would be-
yeah, because it's a very wide range of frequency which operates, so we can use the copper coils to power up the any motor or any device.
Okay, stand by. Let me digest this. What is the RF frequency? 6 megahertz
Wha-
at the top end?
For
So
the
what's the frequency range?
for the fractal antenna from 6 kilo to 600 mega.
Okay. From 6 kilohertz to 600 megahertz encompasses so much RF spectrum that
Yes.
it will interfere with everything in power. So if you are starting to operate this in kilowatts and at 91.5 megahertz, you'll wipe out the entire FM band. So people will know it. In other words, if you put 100 watts in the middle of the FM band and it stops everybody from receiving radio, you're going to get a knock on the door from the FCC. They'll get their truck out, they'll triangulate your position, and they will find you. This sounds like this is you're transmitting power, right? It has to be a power. And
Yes.
You've got a carrier, and it's in the middle of the FM band. Doesn't that strike you as one of those things that might be a practical drawback to your system? Yeah.
But we can, I think there is a possibility that we can tune the frequencies to what the for which we are powering up, for the equipment which we are powering up. So if we know the frequency at which the component is working, maybe we can just like tune the frequency. It is the 6 kilohertz and 600 megahertz is actually the range, the whole broadband range at which it can operate. But maybe there is a possibility that we can tune to a specific frequency.
Yeah,
We can
sounds
use
like
it
you need one frequency.
at which a mechanism can operate. So the next paper is effectiveness of space filling fractal geometry in lowering resonant frequency. So if we use the fractal antenna, we all of us will be expecting some effectiveness. So this paper cites the effectiveness, that the effectiveness of the geometry in lowering resonant frequencies is like is more like a direct function of the current vector alignment, which is similar to the wire layout. So that might be a big reason that we can use it with the vitricity.
Can you take the fractal antenna and mount it in a parabolic focusing configuration so that it only gives you a beam in one direction? Like for example,
It actually radiates
if
in the.
you look at a point source radiator that comes off the tower, the power is inversely proportional to the square of the distance, but the effective radiated power gives you gain that's flat because they don't want to radiate straight up. So they create gain in the plane by adjusting the elements in the antenna. And in this way you can take a 5 kilowatt power amplifier and get a 10 kilowatt effective radiated power because they're tuning the antenna elements during transmission. So with the fractal, we've so far considered the idea that we would just print it on a printed circuit board. But if that printed circuit board were mounted at the foci of a parabolic dish, then you might be able to get a directionality that gives you a substantial gain.
We can do it. There is a paper which I already cited here, but the efficiency is reduced.
Oh,
So it we actually are trying to transmit the power. For example, if we are trying to transmit the power wirelessly in this room, we might just put the antenna in the middle so that it distributes the energy in the whole room, so that every component in the every device in the room is powered up.
Yeah, but it has orientation, right? Because it's in the
Yes.
plane.
No, if we put like this on the table, like
Oh, on the table.
yeah, on the table, or in any like if it is in the center of the home, there would be a wide range with which all the
Don't you want to have two plates that are roughly parallel to one another to maximize energy transfer? Or because if you turn them like this, how will they transfer energy? It's like
They're-
coils in a transformer.
Yes, yes,
You want the coils to be as close as possible, and you want them to be lined up.
yes,
So if you move them apart, certainly don't want to rotate them out of the plane, like one like this and the other like that. The polarization will be all wrong.
yes. The polarization. There would be no power transfer. Chip. So the next paper is an overview of the fractal antenna engineering research. Here they the this paper actually cites has been focused in majorly in two areas. The first deals with the analysis and design of the fractal antenna elements, of how it works, how the operation is done, and how there could be a possibility of transmitting the electromagnetic radiation. And the second concerns about the application of the fractal concepts to the design of antenna arrays. So in the second concern, the thing is, they had cited that there might be a possibility where we can tune the frequency at which a particular system or a device operates, so that it doesn't mismatch with the other frequency bands. So this is in this paper there is the answer about what we are asking before, like how to tune the frequency and to lock a frequency at a specific bandwidth. So that's the, and the next paper is fractal antenna engineering, the theory and design of the fractal antenna. So in this paper there has been an overview of the recent developments in the field of fractal antenna engineering, with a particular emphasis on a theory or on a design of the fractal antenna. So it means that this paper mainly tells us that where the fractal antenna can be used, how we can use it, how it is useful to the public, like the societal impact of the fractal antenna. And, these are some of the papers that I recently got it. So there are some fractal antennas with which there has been a successful experiments for wireless power transmission. So here this article actually analyzes the power transmission capability of the fractal antenna. So there are two types of fractal antennas that this paper had cited. One of them is type of wire and has an efficiency not less than 80%, and another one is of type of plate with a maximum power transmission efficiency of 55%. So it all depends on how the what shape the fractal antenna is. If it is of a wire, we get a maximum efficiency of 80%, but if it is of a type of plate, the efficiency has been reduced to 55%. And this is the fractal antennas for wireless power transmission. This article proposes a fractal antenna to improve the power transmission. So as I had said before, using the plate type of fractal antenna reduces the efficiency to 55, but using the wire type of fractal antenna increases the efficiency of up to 80%. So this paper mainly focuses on the type of wire fractal antenna with higher efficiency, that is 80% of efficiency. So there is the next paper is a Sierpinski fractal based microstrip patch antenna used for transmitting power wirelessly. So this paper uh,
That's sort of like what you want to do.
yes, but this is a Sierpinski fractal antenna. But what I was thinking was the efficiency, the antenna size was reduced to 31.26.
I got a problem with this. Why should it be 2D?
I'm sorry.
Antennas aren't 2D, right? The Yagi antenna has a director, a reflector, and a radiator, the driven element. There are 3 elements in the
Yes.
Yagi antenna. It's a 3D element,
Yes.
right? You've got several focusing elements, perhaps, but you've got the driven element, then there's a reflector, and then there's a director. And you could have multiple directors, and you could steer it around, and it gives you focusing. A Sierpinski carpet, by its very nature, is 2D. But
Yes.
if you use a Sierpinski sponge, then you have a 3D fractal antenna.
Okay.
So why not make a 3D? Does anybody do 3D fractal antenna?
I did not get any. No.
No, I've never seen it.
I have searched it in USPTY and Google Scholar, but I did not find anyone doing that.
Obvious. Isn't it obvious? You should
Yeah.
try these.
So in this paper, it cites about the design and simulation results of the 2.4 GHz microstrip patch fractal antenna. So the main advantage what they achieved from using this Sierpinski fractal antenna is that the size of the antenna was reduced by 31.26%. It is a considerably high rate to reduce the size of the antenna, and also the simulation was done using a Zealand incorporated IE3D software. So that's what the paper cites. That's it.
Okay, so at the end of these things, you should have your list of papers. And you
I
should be citing the
had-
papers with like an author in angle brackets, and that's what we'll expect to see when you
Yeah,
do
but,
your report.
Yes, I put some.
Yeah, I see you got a couple in there.
Yeah.
But you want to do a proper
Okay.
citation
Yes,
as if you're
yes.
going to write a report on it.
Yes,
And then list all of your citations at the end.
I got it.
We are out of time. Thank you for your presentations. I think they are all very promising and things are coming along very well. I'm looking forward to your questions for next week, and I'm going to plan on doing a lecture on ethics because I think if you haven't had a course on ethics, we should at least have a little bit of a lecture on it so that it can be included in your report. Have a good day. It looks like it's a nice day out. Somebody told me yesterday it was going to snow, but they were wrong. Thankfully. And they should be wrong because it's spring. And so we're done with that now.